So here's one of the missing pieces of the puzzle, and that's the notion of uniform continuity. I claim that's really the key thing about test functions that's going to push this a little forward and tell us that it really is okay to slide them back and forth when we're integrating against some other function. We're still in a bit of a sidelight here because we still have to go back to general distributions, but this is a really great digression to come up with these ideas. So let me write down the definition of ordinary continuity, and then I'll talk about briefly, again, this is worthy of a lot more discussion and a lot more practice in particular. That's trying to be you there. But I'm going to make it kind of brief this time. So ordinary continuity. So f is continuous at a particular x naught. And so notice we've fixed the place where we're testing continuity in advance. Very different from the uniform idea that we were talking about before, and we'll see how it's going to change in a minute. If for every epsilon greater than 0, so every error tolerance in the output, that's going to be like so. Here's x naught, and here's f of x naught, and I say, okay, I'm going to allow you a certain amount of error in the output, and I'm going to challenge you to come up with a delta such that that's going to be an error tolerance in the input, such that whenever x is within delta of x naught, then f of x is within epsilon of f of x naught. Okay, that's the definition of continuity at a specific point. And here's the deal. The relationship of epsilon to delta is totally allowed to depend on the x naught that you choose. And then what you often do is you say, okay, and then f is continuous on all of R or on a whole interval or on a whole set, if this works for every point. But it can work for every point totally independently, and each point can have a very different relationship between delta and epsilon. So for example, in this picture, x is not changing very fast. Its slope is not very big. I drew it differentiably. It doesn't have to be for this kind of idea, but it's a good way to think about it. Its slope is not very big here, and so in order to get a certain amount of error of accuracy in the output epsilon to be in this band with the horizontal lines, I didn't have to be very strict about the delta. A fairly wide delta works, and any point reasonably near x naught gets me in that epsilon band. But what if we had the same epsilon tolerance around f of x1? Okay, so I'm going to erase a lot of that stuff with my finger. Okay, so I've got that same kind of epsilon tolerance around x1. And can I have that same width? It was pretty wide. If I go too far, if I go the same amount delta left or right, then this slope, this steep slope, is going to pop me out of that band. And so I'm going to try to use a delta that's like the same size, and instead I'm going to get something where the values go out of the desired epsilon band. Here's epsilon again, even though I'm staying within delta of x1, if I use the same delta epsilon relationship that I was using in this case where it wasn't so steep. So now that's fine as far as ordinary continuity is concerned. So what if the relationship was different here? Okay, so I just pick a different delta that's a little tighter for a given epsilon, and we go on our merry way. But here's uniform continuity. Okay, f is uniformly continuous, and you don't just do it at a point on, I'm going to say all of R, but it really can be done on a subset if you just don't care about off that subset. So if for every epsilon greater than 0, there's a delta such that if x minus x naught, and I'm going to take away the x naught because I don't want to make it feel like there's a fixed x naught and then x is getting close to it. It's really just an x and a y, okay? Such that, and I'm going to make the quantifiers really explicit, for all pairs of points, x and y, in R. Okay. So here, you give me the epsilon greater than 0. That's always, that's where it starts, right? And then I have to pick a delta And you don't let me know where the x's and y's are going to be in advance in order to pick the delta. One particular delta has to work for any particular epsilon, but it has to work for all x and y simultaneously and uniformly. Okay. And so that's the definition. It looks a lot like the definition of continuity. Of course it looks like it because it's a variation of the idea. But the uniform idea is a big deal. This is one of the big stumbling blocks, excuse me, when people get to a real analysis class, thinking about these kinds of subtleties carefully enough and these kinds of distinctions. Okay, so again, worth a lot of work, but we're going to try and do just kind of work through a few examples and see how this works in our case. Okay, so let's assume that our function g is uniformly continuous. Oh, one thing I probably should have put this in the PDF. Before I do this, what about g of tau equals tau squared? Okay. Now, clearly g equals h. That's not even ordinarily continuous, so that's not uniformly continuous. G of tau equals tau squared. It's a good exercise to show that that is continuous but not uniformly continuous. Basically because that slope is unbounded. It's not uniformly continuous if you consider it on all of R. If you're on a bounded interval, if you just continue it from like consider it from minus 1,000 to 1,000, it'll work. It'll be fine. But it's a good exercise. I don't think I'll do it right here to show that that's not uniformly continuous. And that's an explanation of why when we slid it back and forth, it was causing problems. Okay, so let's assume G is uniformly continuous. I don't know yet that test functions are, but we will show that, and it's not super hard. Okay, and then it's very easy to see that G check is also uniformly continuous. You're just flipping it. Hopefully that's pretty obvious, even if the details maybe you have to write them down. Okay, and then I want to show that that's enough. In fact, it's pretty much equivalent to saying that when we shift a function left or right, oops, that's the variable t, that this converges uniformly if the t's are going to t naught. Okay. Well, okay, so all of these proofs start with the same sentence, let epsilon greater than 0. Okay. Then we know by that uniform continuity there is a delta greater than 0 such that for all, okay, so here's what I want to show. I want to use this condition that g of something minus g of something similar is small, in other words, is less than epsilon. Okay, but what I actually want to show, okay, g check t, I want to plug in a tau into that kind of expression. Oh, I know what that does. It's g of t minus tau, and this is g of t naught minus tau. Okay. So these are the kinds of things I'm actually going to be comparing. The t shifted g evaluated at g check evaluated at g at tau, and the t naught shifted g check evaluated at tau. Okay, can I actually make this a true statement? Yeah, there is a delta greater than 0, such that for all t and t naught, as long as t and t naught are close, it's a delta. Okay. Then I claim we can assert this. Why is that? Well, if t and t naught are within delta, then certainly t minus tau and t naught minus the same tau are also within delta of each other. So these are just the x and the y in the definition of uniform continuity. Okay, so that's really the key observation, is that taking two functions that are slid by similar amounts and evaluating them at the same point, so that's this guy evaluated at tau and this guy evaluated at tau, that's the same idea as the uniform continuity idea. It's the same idea as taking two fairly arbitrary points, call them x and y, and evaluating the same function at those two similar points. Okay, so it's just because this is equivalent to these guys being within delta as well. I'm just subtracting tau from both of them. Okay, alrighty. So, so that says that this. I'm just going to rewrite this. This is just g tau. Actually, this is just g. It's just g check tau. Did I do the checks right? I don't know if I put the checks in right. Yeah, I'm not sure if I'm putting the checks in right. But as I said, it doesn't matter. Okay, So that's g check t of tau, and that's g check t naught of tau. And that's what I wanted. That's uniform convergence. That's the two different functions evaluated at the same point, which was very closely related to the same function evaluated at different points but slid left or right from each other. What this really is proving is that another way to say the definition of uniform continuity is that when you slide it a little bit to the left or right, and then you slide it back and you let that t approach t naught, that you get a uniformly convergent family of functions. So they're intimately tied together. Okay, I hope that wasn't too abstract. Maybe should have done more examples, but leave a comment. I can always make an extra video. Okay, so now, finally, to finish off this one subpart of this one problem, our test functions. Actually, yeah, and let me look at a little roadmap here. There's a lot of intricate stuff going on. Okay, so I'll do this in a second, but we're gonna show this. Okay, test functions are uniformly continuous. Okay, therefore, if g is a test function, then we just saw that these guys converge uniformly. And when we saw that if a sequence of functions is converging uniformly, and then I integrate it against some other function, well, that's a tau, that's exactly the condition that you want. It's the best condition to make an easy proof of convergence of an integral. It is not absolutely necessary, and a lot of the Lebesgue theory of integrals, which we're not doing quite yet, I'd love to get to it, and like video 100 or something, is designed to show that integrals converge even if you don't have uniform convergence of the integrands. But boy, it's a lot easier when the integrands converge uniformly. Okay, and so that converges to the idea was that was going to convert was continuous because the values it gives don't change too much when you change the t parameter. Okay, and that was still not nearly done, but it gives hope that remember this conundrum was we have these new and old versions of convolution that we'd like to show that they're equal, and it certainly starts to suggest that at least this new version is giving nice functions. Okay, and again, we actually really want to replace this with a u. Okay, so we're really in the early stages here, but we're playing with a lot of good ideas. Okay, so I just wanted to remind you of the roadmap. I hope it didn't take too much extra time to do that. Okay, so our test function's uniformly continuous. Okay, well, yes. Okay, so g is all I'm going to use is that it's continuously differentiable. The idea, I've alluded to this already, is that if you know your function is differentiable, the only thing that can really screw up uniform continuity is if you let that derivative get too big for too long, kind of go off to infinity. Okay, it's continuously differentiable and it's compactly supported. There's no possibility to go off to infinity at all. And the fact that it's continuously differentiable on a compact set, that means that that derivative is going to be bounded. Okay, so let n be the maximum, and this maximum really does exist. It's a continuous function on a closed and bounded interval. This is like a theorem that's actually in Stewart's Calc 1 book. Nothing super technical. That's just the maximum slope of the function. Okay, and then good old MVT. MVT is usually often misunderstood. It's often like, oh, you have to find some special point where the slope matches the tangent slope matches the secant slope. Let me call it the corollary of MVT. It's that if I have, and let's do the maximum of, well, I think it should be the absolute value. I think I missed that in my notes, so I should go back. If you know the maximum rate of change of maximum instantaneous rate of change of a function, it means that if you look at the overall rate of change of a function and just look at the size of that, that's also less than or equal to n. The way I like to say this, I won't go into too much depth on this. The way I like to say it is, if your speedometer, if you never see your speedometer go over 60 miles an hour, then you're not going to make any trip that averages more than 60 miles an hour. That's 95% of the time. That's what you use the mean value theorem for. Okay. So in other words, the difference between these two values, oh, hey, that's what we want to be small to show uniform continuity. That's less than n times, oh, the difference between the inputs, and that's what we can make small in uniform continuity. Okay, so let's just let delta equal epsilon over n. Change the tolerance in the input is tolerance in the output divided by the sensitivity of the function, basically. Okay, if that's how you choose delta, that's going to be less than, and x minus y is less than delta, this is going to be less than n times epsilon over n, which is epsilon. And we're good. Okay, I should have drawn a picture here, but it's the same picture. If I've got this function, and I know the worst case scenario is a certain slope n, then the relationship between the epsilon tolerance in the vertical and the delta tolerance in the horizontal is just going to be that slope n at worst case. So it's a really good example of a fairly simple use of mean value to get what we want. Okay, so yes, test functions are uniformly continuous. Okay, therefore when you slide them left or right, they uniformly converge. Therefore, when you integrate against functions, they really do what we want, and we get continuous convolutions. Okay, all largely just good excuses to introduce these really great concepts. But then we'll see how these concepts come back in the rest of this handout, specifically to understand what we really want as the definition of a distribution.